Suppose f and g are partitions of a set A. We define a new family of sets f dot g as follows. F dot g is going to consist of all the elements z in the power set of A, so all subsets of A which are non-empty and which are basically formed by taking the intersection of one set x from the family F and another set y from the family G. And we're supposed to prove that this new family of sets f dot g is a partition. Okay, so let's draw a picture of what's going on here. We have a single set A with two different partitions on it, so maybe I can draw that set A a couple times. Okay, just sort of two copies of the same set here. And the first time I have a partition F, and so maybe imagine that this set A is a set of students in a class, and maybe F is going to partition those students into whether they like red best, or green best, or blue best. Okay, and so the partition F has three elements, namely these three subsets of A. And then G is a partition on the curly G is a partition on the same set A, but maybe that partition splits A up into two pieces, the male students and the female students. Okay, so the partition, whoops, that's kind of a funny G. The partition G has two elements, namely these two subsets of the set A of all students. All right, and then we're forming a new family of sets f dot g, which they're also all going to be subsets of A, right? So let's draw another copy of A here. They're all elements of the power set of A, and they're not empty, and they're formed by intersecting an element x from F over here with an element y from G. Okay, and so basically, if we split it up like we are in the partition F, and then we also split it up like we do in the partition G, then you see we get sort of six possibilities, right? We have this corner up here, which would be the students who like red and who are male, so you can sort of label that by RM. And then right here would be students who like green and are male, and blue and male. Actually, I should be writing sort of R intersect M here, and G intersect M, and B intersect M, and so on. But you see what I mean. And then these are students who like red and are female, green, female, and blue, female. Okay, and so most likely our new family f dot g consists of these six subsets of A. F dot G. Okay, good enough. The only thing that might interfere with that happening is if any of these sort of intersections happen to be empty, right? Because then they don't count. Then they're not elements of f dot g. So if it just so happens that there are no students in the class who prefer green and who are male, then f dot g would have maybe just these other five. All right. And so we're supposed to believe that f dot g is a partition, right? That the union of the sets is A, which appears to be true. And they're pairwise disjoint, meaning they don't have any overlap with each other, and they're all non-empty. Okay, and we're only choosing to keep the non-empty ones. So this sounds reasonable. Let's go ahead and prove it. We are given f and g are partitions. We're proving f dot g is a partition. So each time we get three pieces of information, and we're trying to prove these three pieces of information. Okay, so first of all, let's take the union of f dot g equals A goal, and we're going to use the similar givens from f and g. Okay, so we want to prove that for all z, again I dropped that here because, well, we're used to it being there by now. For all z is in the left side if and only if it's in the right side. Okay, and so okay, let us do that. And I think I tried to do that with givens and goals, and I realized it was pretty much the same in both directions. In that case, I like to do a chain of if and only ifs. So let's try that. Okay. I have an introductory sentence up here. In order to prove that it's a partition, we have to show these three things. So you can leave that out if you want, but it might give some helpful direction to our reader. And okay, first we're going to prove the union statement. The union is A. We're going to show that z. We're going to show this. Z is on the left side if and only if it's on the right side. So start out with z on the left side. And we got a bunch of steps here. Let's try and justify each one of them. First of all, this is just definition of union, right? Z is in the union of this family if there exists an element of the family such that it it contains little z. And then here we have, this is a bounded quantifier, right? It's just a shorthand for there exists z such that z is in f dot g and little z is in z. All right, and now here we would love to get rid of this dot notation. So we look over at the definition of f dot g and we see what does it mean for z to be in there, right? And it means, okay, well, z is an element of the power set of A. I didn't explicitly write that here, but we can keep that in mind. Basically, everything's a subset of A here, so I'm not too worried about that. And then, more importantly, we have that z is not empty, and this existential statement is true. So that's what you see me writing here. And then I've also carried down the z and z from up above. All right. Now let's see what we could do next. I'm going to pull the quantifiers all out front so that those kind of get out of the way and we can actually see what we have. And good, so I've done that. And then you notice I've also dropped the z not equal to the empty set statement. In fact, maybe I should have mentioned that one first. And the reason I can drop that is because over here I have that little z is an element of capital Z, right? So under the assumption that's true, this statement over here is redundant. Okay, so we can sort of add or subtract it at will without changing the overall statement. All right, so we dropped that one, we pulled the quantifiers outside, and now we have these two statements in here connected by an and. And well, I'd really like, if you kind of work backwards, you realize you really want to get rid of this z equals x intersect y statement somehow. And so my method for doing that is to, well, since I know that's true, I can replace this capital Z by x intersect y, right? And now there's no capital Z's in this statement here. And so there exists z quantifier. I can just put that only on the first half of this conjunction, like you see here, with this outside. And now if you look at this existential statement, there exists capital Z such that capital Z equals x intersect y. That's a tautology, right? I mean, what's a capital Z that works? X intersect y. Right? We have an x and a y from out here. And so that's just always true. So we have a tautology and this statement. And in that situation, you can just drop the tautology. So it's gone. We're down to here. We don't have any capital Z's left. And now we can, what? Well, here we have some more bounded quantifiers. So let's sort of peel off the x in f and the y in g. And we can also split this statement up into z in x and z in y. And then I've just gathered the two statements about capital X together and the two statements about capital Y together. Okay, so about three things going on there at once. And all right, we have there exists y quantifier, and the only place capital Y shows up is in the latter two statements, so I can go ahead and put the quantifier just on those. And similarly, the only statements out of these four with capital X's are the first two, so that there exists x quantifier can go just on those. And now I can turn them back into bounded quantifiers again. And there exists x in f such that z is an x, and so on similarly for y. And those two statements are just exactly the definition that, well, z is in union of the family f and z is in the union of the family g. And remember, we were assuming that those two unions are equal to A because f and g are partitions of A. And so that's where we use our givens. So we can replace each of those by A. And so we have z in A and z in A. And that certainly is equivalent to just saying the same thing once, right? That z is in A, which was our goal. So that was kind of a crazy dance, but we got there. All right. So that was the first piece, and now we got to show that f dot g is this family's pairwise disjoint, and we're going to use that f and g are. So we remember the definition of pairwise disjoint. Basically, if we have two different sets in this family, z and z prime, then if they're different, they have to be disjoint. Right? They can't overlap at all. Okay, so let's write out some definitions over here as well, and then we'll take z and z prime to be arbitrary elements of f dot g. So I'm kind of abbreviating that there. And then we'll do direct proof. So actually, we won't do direct proof. I would rather assume that z and z prime are not disjoint, right? So that they have an element in common, and then I'll prove the negation of the antecedent that z equals z prime. Okay, so I'm proving the contrapositive here. Okay, and then we got to use our definition of f dot g again. So z being in there gives us the first line, and z prime gives us the second line. And I'm being careful to use different bound variables x prime and y prime from the x and y up here. There's no reason those have to be the same. And we also have z and z prime are non-empty, so there exists some element in both in the intersection. And now it looks like we have a bunch of existential instantiation to do. So for this one, we get an x naught and a y naught in f and g, such that z equals x naught intersect y naught. And then from the second one, we get the x naught prime and the y naught prime, such that z prime equals the intersection of those two. Okay, so I've kind of mixed these two up, rearranged them in a more convenient manner. And then we have some z naught, which is in the intersection. And now if we try to combine those three things we just came up with, well, we know what z and z prime are, so we could replace these guys down here by x naught intersect y naught and the other intersection too. And okay, so that's going to give us that z naught is in basically all four of these sets here, right? X naught, y naught, x naught prime, y naught prime. And so I can split that in half by splitting up a conjunction to get them in a form I want. And well, look, we haven't used the pairwise disjoint stuff up here, and so there's something up there about these intersections being empty. But we know that these intersections both contain an element, right? And so we know they're not equal to the empty set. And so now if we bring down via universal instantiation these conditionals, we can use modus tollens in each case, combined with our statements down here about these sets not being disjoint, to prove that they are in fact equal. And that's what pairwise disjoint means. If two sets are not disjoint, then they must not be different, or they must be the same. And to finish up, we remember what the definition of z and z prime was. Well, intersecting the two left-hand sides here and the two right-hand sides, we get that equality at the bottom. And the left-hand side is exactly z. The right-hand side is exactly z prime. So we have our goal. Okay. And here you see the proof that f dot g is pairwise disjoint. We let z and z prime be arbitrary elements of f dot g. We're going to prove the contrapositive. Well, we're going to show that if-then statement by proving the contrapositive. And here's a summary of what we did. All right. So you can pause it and read that if you like. And that leaves us with just the last part, namely that every element of this family is non-empty. Okay. And so we'll take an arbitrary element z of f dot g, prove it's non-empty. Okay, and once again, using the definition, we know that z is not empty and it's formed in this way, and just the first half of that gives us exactly what we need, so we don't even have to worry about the rest. Okay, so that takes care of that one. So all I said in the proof was, finally we note that every z in f dot g is non-empty by definition, which is what we need. And so we're done.